Today, I'd like to talk to you about the 2022 Nobel Prizes in Chemistry. They went to organic chemists on click chemistry. Click chemistry is a part of synthetic chemistry. Another major part is total synthesis. Total synthesis was the dominant form of organic chemistry in the 1990s. The theme of total synthesis is complexity is good. The bigger the challenge, the better they like it. Around about 2001 and 2002, click chemistry emerged, and it was operating under a different paradigm altogether. Simplicity is good. Chemists doing click chemistry like to do it in one step. They like their reagents to be cheap, and it should be scalable and easy. Anyone could do it. Even I could do a click reaction. It's robust. It works for a lot of different substrates and can be catalytic. In 2002, I remember talking to synthetic organic chemists, and some of them ridiculed click chemistry. This is not so important. It's just an easy reaction. The idea that we'll get a Nobel Prize in 2002, no. In 2022, it did. So what changed? What was the evolution of click chemistry? First of all, it was enabled. And who enabled it? Well, the first person to publish on click chemistry was Morten Mendel. Morten Mendel is a Danish scientist. He specializes in solid phase synthesis, and he was reacting alkynes on the solid phase with azides in solution. Now, that reaction, it gives a cycloaddition, a 2+3 cycloaddition, we call it. But it can happen in two ways. Two regioisomers can be produced. And what Morten Mendel found with his group is that in the presence of copper, one regioisomer would be formed almost exclusively and in high yield. So the first well-known paper by Morten Mendel was this one in JOC, Journal of Organic Chemistry, and it was published in 2002, submitted in late 2001. But actually, Mendel talked about click chemistry earlier in 2001 at a meeting in June. What did Mendel say when he won the Nobel Prize? He said, I am very, very happy. In Britain, we like the art of understatement, but it seems like the Danes know about it as well. Mendel didn't really take it into the solution phase that much, but Barry Sharpless did. He illustrated the practicality of the reaction. Barry Sharpless published in 2002. Apparently, the studies were going on concurrently with Morten Mendel. He's won 2. He's the only living person to have 2 Nobel Prizes, one of 5 that had ever done so. Stop the video. Pop quiz. Who else has won 2 Nobel Prizes? And I've given you a clue. They're all dead. Have you done it yet? No cheating. Well, they are. Marie Curie. She won one first in physics and then in chemistry. Linus Pauling went the other way. He did chemistry first and then peace. And then Fred Sanger, of course, and John Bardeen, a physicist. Isn't it remarkable that 4 of the 5 people to have won 2 Nobel Prizes are chemists? Both Mendel and Sharpless contributed to enablement. Sharpless showed the practicality in solution, the importance of the chemoselectivity of the reaction in chemical biology was discovered by someone else. Now, what do I mean by chemoselectivity? I mean, if you mix an azide and an alkyne, they probably don't react with anything else in a biological system, at least. It was Caroline Bertozzi who said, I'm going to use this for biological chemistry. Caroline Bertozzi studies glycoproteins and sugars on cell surfaces. So she engineered cell surfaces with azides on them and could add things to the surface of the cell with an alkyne. But there was a problem to overcome, because in the presence of copper, cells do funny things. In the presence of a little bit more copper, they die. And of course, that's not ideal. So what Caroline Bertozzi did is she said, let the alkyne be a strained alkyne, perhaps one in an 8-membered ring, cyclooctane system. A cyclooctane is so strained it can't wait to get out of that environment. With an azide, without copper, it undergoes a 2+3 cycloaddition straight away. If Caroline Bertozzi could put an azide on the surface of the cell, she can add reagents with, for instance, cyclooctane, and add to that azide chemoselectively. Nothing else on the surface of the cell would add. There were critics about click chemistry, and what they missed, this mantra that complexity is good is fine. It was a challenge in total synthesis to make bigger and bigger molecules. But the flip side of that is that simplicity is bad, and simplicity isn't bad. That doesn't follow. It's illogical. Because anyone who thinks that simplicity in organic synthesis is bad largely misses the point of doing organic synthesis altogether. And that is, we make things because we need them. If the reactions are so complicated and low yielding, we can't make much. So click chemistry came along and it flew in the face of the sentiment of total synthesis. Simple, straightforward, high-yielding reactions can be very precious, and they proved to be very precious in the last 20 years. Congratulations to Walter Mendel, to Barry Sharpless, and to Caroline Bertozzi, a great achievement in winning this year's Nobel Prize. Thank you all for listening. I would like to thank Fulbright Malaysia, the Malaysian American Commission on Educational Exchange, MACE, at the School of Pharmacy, University of Malaysia. I have an ebook on bonding and hybridization. It is published electronically on Mac iBooks, and soon I hope to find the time to put it on Amazon Kindle. I have workbooks in hard copy for sophomore organic chemistry. I call them Sophomore Organic Chemistry by Inquisition. You can buy them from my website, www.byinquisition.org, and also from Amazon. But at my website, the answers are posted there too. So students who work through these problems can check. I also have Organic Chemistry by Inquisition #1, General Methods. That's a more advanced workbook for graduate students. If you buy it, I hope you enjoy it. Thank you for listening. Bye-bye.